Today we're going to talk about series circuits and also derive an equation called voltage divider equation that you can use to find voltage across series resistors. So here's a series circuit, and what makes it a series circuit is that there's only a single path for current to flow. So as you can see, we have three resistors along with the voltage source, and this current is flowing in this single path in the direction that I'm showing here. And as I mentioned in an earlier lecture, the current is the same through series elements. So this current here is the same through the voltage source and all three resistors. And again, you can prove that by doing KCL at each of these nodes. And because current in equals current out at a node in a circuit, you would see that you get the same current throughout this single path. So here in the derivation for voltage divider equation, you start with KVL, and this is just written so voltage rises is on the left side of the equal sign and voltage drops are on the right side of the equal sign. Remember, voltage rise is when current flows through an element, voltage goes minus the plus. So here's the voltage rise here, and then each of these resistors have a voltage drop because as the current flows through a resistor, we go plus to minus in voltage. Now, using Ohm's law, we substitute in for each resistor voltage I times R. So V1 is the current I times the value R1, V2 is I times R2, and V3 is I times R3. And now we can factor out the I since it's all the same current. And what this shows is that these three series resistors can be represented as a single resistance called the R equivalent. That's the sum of the individual resistor values. And this is valid no matter how many resistors you have in series. So this example has 3, but whether you have 2, 3, 4, umpteen hundred, whatever it may be, you can always get the REQ of series resistors by just adding their individual resistances. So here now we substitute in the REQ, and you can solve for I and show that the current that's flowing in that series circuit is just the voltage source value divided by that REQ. Now before I do the next step, let me just mention that this derivation is also shown in our text, in the Alexander text. Now to get the voltage across each single resistor, we can do I times R, where we substitute in this I. Okay, so we just substitute in V over R equivalent for I, and now we end up with voltage divider equation. See, voltage divider equation is showing that the voltage across a resistor is equal to the voltage across the series combination times a ratio of resistances, where the denominator of that ratio is the R equivalent of the series resistors, and the numerator of that ratio is the resistor you want the voltage for. So V1 is the voltage across R1, so that's why R1 goes in the numerator. Likewise, V2, R2 is in the numerator, V3, R3 is in the numerator. So next, let's do a problem where first we solve it without voltage divider equation, and then we solve it using voltage divider equation, just to show we get the same answers. Okay, so here we have three resistors, just like the diagram we did the derivation in, just now we have numerical value. So we would start off, okay, finding the REQ, okay, which is just adding those resistor values up. So 18 plus 6 plus 24, that's 48 ohms. Okay, then the current I would be the source value of 12 volts divided by REQ. So that's 1/4 of an amp. And then the voltage across each resistor would just be its resistance times that current, R times I. So the voltage across the 24 is going to be 24 times 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 . 1/4 so this would be 6 volts. Okay, and then the voltage across the 6, it's going to be 6 times a quarter one and a half volts, and then the voltage across the 18 ohm. Okay, I'm just going to write the answer, but it'd be 18 times a quarter, so 4.5 volts. Also, we know it's got to be 4.5 volts because the voltage drops across the resistors have to sum up to the source voltage, right? And 4.5 plus 1.5 plus 6 is the 12 volts of the source. Now, also, just to be complete here, let's put in the polarity of the voltages for the resistors on the diagram. So remember, higher end voltage for resistors always on the end where the current enters. Okay, so that's what our polarities would look like. Okay, so you see those are our answers. We didn't use voltage divider equation to find the voltage across the resistors, right? We just did REQ and then used Ohm's law a couple of times. But now, if I'm going to use voltage divider equation, okay, so voltage divider equation, okay, see I can go right to finding the voltage across a resistor. See, I wouldn't have to do these first couple of steps because it's built into the equation. I mean, you saw that in the derivation, those equations were the first couple of steps of the derivation. So you see, using voltage divider equation, the way we get the voltage across the 24 is that there's 12 volts across the series combination, then it's times a ratio, where in the numerator would go the value of the resistor I want the voltage for, so the 24, and in the denominator would go the REQ. Okay, so you see 24 over 48 is a half, so we would get 6 volts, which is the same as what we got over on the other side of the page there. And then using voltage divider for the 6 ohm, we would have 12 times 6 over 48. Okay, so 12 over 48, that's a quarter, so 6 over a quarter. One and a half volts, see? So same answer as before. And then voltage divider for the ohm. Right, we got 12 times 18 over 48. So now you're going to get 18 divided by 4, which is 4.5. Okay, so either way gives you the same answer. So voltage divider, a lot of times when the problems get more complex, you'll see that shortly we'll get the circuits that are more complex than these basic circuits we've been looking at thus far. And a lot of times voltage divider equation can save you time finding voltage across series resistors. Now, before we leave this, I just want to point out one other, and this is really a conceptual type of thing, and that's, notice that the largest resistance, okay, 24 ohms, had most of the voltage. Okay, see, the larger resistor had 6 volts, the smallest resistor had the smallest amount of voltage, 1.5, and then the middle resistor had 4.5 volts. And you see, this is always true. It's always true that in a series connection, the current's the same and the voltage splits up or divides. That's why it's called voltage divider, to find how the voltage splits up amongst the series resistors. And it's always true that the largest series resistance has most of the voltage. Okay, and the smallest series resistance will have the least amount of voltage. See, that's always true. And I mean, you can see it mathematically in voltage divider equation, right? Just looking at the ratios here. But I think it's good to have a conceptual understanding. And this goes back to, our analogies that current is a flow, right? It's a continuous movement of charge. And um, voltage we think is pressure, and then resistance is opposition to the flow. So if you just put some of this together here, it should make sense to you that in order to maintain a constant flow, because remember the current is the same in a series circuit, right? So there's constant flow here. Well, in order to maintain that constant flow, it makes sense that the largest opposition would have to have the most pressure, right? So to maintain that constant flow, our largest resistance has to have most of the voltage. Okay, and likewise, the smallest resistance would need a smaller amount of pressure to maintain that constant flow. So I think, again, just thinking about the analogous quantities that we've come up previously gives a better understanding, because not only can you understand it mathematically, but also conceptually, hopefully.